My name is Pierre Martinez.
And I'm Antonio Flores Jr.
Today we'll be presenting our final project for CS 5344 for computer networks and distribution systems. Our project is called the Smart Campus Network, and the goal is to design and simulate a secure, scalable, and realistic network for Southern Methodist University using Cisco Packet Tracer. Throughout the project, we applied core networking principles, configured enterprise-level devices, and implemented modern security features, all to make something that reflects how real university networks operate.
Yeah, and at its core, our project was just about taking SMU's large campus network and just making a smaller but still realistic version of this. And to do this, we just focused on four main buildings, the Junkins Engineering Building, the Fondren Library Building, the Cox School of Business building, and the Hughes Trigg Student Center building, which we also treated as our central control hub.
To bring it all together, we implemented technologies such as VLANs to separate traffic, DHCP for automatic IP assignments, DNS for name resolution, access control lists to manage permissions, and WPA2 for wireless security.
Yeah, and all these components work together under a hierarchical structure. This is a setup that we intentionally followed because it makes large networks just more reliable, easier to manage, and it makes them easier to expand in the future.
So our motivation came from SMU's growing need as a newly established R1 research university. And so a network this size has to juggle three big things. One, performance, two, reliability, and lastly, security. And so we tackled that by using VLANs to separate users from students, faculty, and labs into their own areas. This keep this keeps the network organized and improves performance.
Yeah, and for reliability, we just use the spanning tree protocol or SCP to help us prevent loops and ensure that the network stays up, even if one connection fails. For security, we added access control lists to isolate sensitive management data from public or student access. And together, all these pieces just form a layered and secure system that will perform well even under heavy use. And so when we started designing the network, we followed the standard three-layer hierarchical model. It's something that's used in almost every large organization today, just because it divides the network into three layers: the core layer, the distribution layer, and the access layer. And the core layer sits right at the center. You can think of it as the brain or the backbone of the entire network. And in our setup, the core layer was a layer three switch that handled all inter VLAN routing, DHCP management, and DNS resolution. So anytime that packet moved from one building to another, it passed through that core switch.
Next is the distribution layer, which acts like the campus highway system. And so it connects every building to the core using high-speed fiber links. This setup makes the network scalable. So if SMU ever added another building, then we can easily connect it without having to redesign everything. Finally, there's the access layer. That's where students, professors, and devices actually connect. This layer includes our layer 2 switches inside each building, and they hook up all the PCs, all the printers, and wireless access points. It's the part of the network that people use every day, even though they don't realize how much is happening behind the scenes.
Yeah, and by dividing the network into these three layers, we made each one responsible for a specific job. The core handles routing and services, the distribution connects buildings, and the access layer connects users. It's just like a city. Highways move traffic between districts, main roads connect neighborhoods, and local streets just get you to your front door. This separation makes the whole system easier to manage, troubleshoot, and scale.
Each VLAN in our system represents a different building. And so we set VLAN 10 for Cox, VLAN 20 for Fondren, VLAN 30 for Junkins, VLAN 99 for management, and lastly, VLAN 200 for servers.
Yeah, and every VLAN has its own subnet and default gateway configured on the layer 3 switch, which allows them to communicate through inter VLAN routing. This is also just called a router on a stick setup.
We use DHCP to automatically assign IP addresses within each subnet and DNS to handle host names. This made communication seamless across all buildings without having to manually configure each item.
Yeah, and the result is just a clean and organized network where departments stay different, where the buildings stay separate for security, but they can still also share resources when needed. Yeah, and to make our simulation realistic, we use one layer three switch at the core, 3 layer 2 switches for building access, and 2 servers, one for DHCP and DNS, and another for IoT and future features. We had 12 end devices, 2 wireless access points, one Cisco ASA firewall, and a Cisco 2911 router that represented the internet.
And this setup closely matches what you would find in a real university network. The balance of routers, switches, servers, and wireless access points all working together. And so each piece has a clear job, and all of them rely on each other to keep the system running smoothly. So security was a major part of our design. We started with the VLAN segmentation to isolate traffic between departments, keeping private data separate.
We also implemented access control lists to control what each VLAN could access. For example, blocking building traffic from blocking student traffic from reaching management networks. On top of that, we added port security to limit how many devices could connect to a single port and to block unauthorized MAC addresses.
For wireless, we enabled WPA2 encryption, ensuring that Wi-Fi connections were secure and encrypted. Together, all these tools, VLANs, ACLs, port security, and WPA2 create layers of defense that protect both users and the network itself.
Yeah, and so while security is important, we thought that reliability was just as important, and because of this, we use dual fiber links between the core and the distribution layers to make sure that the network would stay up even if one connection fails.
And so the SDP manages those links automatically. It prevents switching loops. And so if one link ever goes down, SDP activates the backup almost instantly.
Yeah, and that means that the network can recover in seconds without the user ever noticing a problem. It's the same kind of fault tolerance that's used in enterprise systems that can't afford downtime.
And so once everything was set up, we ran a series of tests to make sure that configuration actually worked. And so we used ping tests to confirm that all VLANs could communicate through the core switch.
And we also tested DHCP and DNS and confirmed that every device received a valid IP address and that they could resolve names properly. We also tested our access control list, which we also tested our access control list. We restricted VLANs couldn't reach protected ones. This is exactly as we intended.
So for redundancy, we simulated a link failure and verified that SDP immediately activated the backup link, and we made sure our wireless connections were stable, secure, and correctly assigned to their VLANs.
Yeah, and in the end, everything passed. We got the system working like how we wanted. It's fast, secure, and reliable.
And so one of our biggest challenges came when we were setting up the laptops. They looked connected, but they weren't getting any IP addresses through the DHCP. And so every time we ran the simulation, no packets were being sent or received. And so we had to go through every part of the configuration. We had to check the VLAN assignments, we had to verify default gateways, and we had to make sure the DHCP pools were correctly linked to their subnets.
And this just took a lot of trial and error to finally spot the issue. At one point, we just realized that a single switch port hadn't been assigned to the right VLAN, and this alone just stopped everything from working.
And so the challenge ended up being one of the most valuable learning experiences in the whole project. Even if everything looks correct, one missing gateway or DHCP relay can completely break the network.
Yeah, and this just taught us about patience and teamwork, I guess. We had to constantly test, double check, and communicate and talk to each other when trying to pinpoint the issue. By the end, we ended up fixing the problem, but we also developed a much stronger understanding of how each layer of the network depends on the others. I guess this is just a reminder that building a network isn't just about connecting cables. It's also about connecting people and trying to solve problems together. And just for a summary, our campus network successfully recreated a scaled down version of a real university system. It's secured, layered, and flexible enough to grow as the campus itself would grow.
And so we showed how VLANs, ACLs, port security, and redundancy can all come together to create a strong, stable network foundation. If we were ever to expand on this, we'd add VPN access for remote users. We'd add syslog for network monitoring and SNMP for centralized management.
And overall, this project just taught us about how to configure this project didn't just teach us about how to configure routers and switches, but it also taught us how to think like network engineers. We had to plan, test, and keep improving our system step by step.
Thank you all for listening. Now we're going to show the simulations. So now we're going to start by testing communication between buildings. And so right now we're going to go to the Cox business building and ping a PC in Fondren to show that inter-VLAN routing is working.
Yeah, and here we can see that we got the reply, which means that it is working. So we've established that this test has passed. Because it'll take us a little longer to get the other three replies, we'll just cut this test short and move on to the next ones.
Next, I'll demonstrate Wi-Fi access, and so each building has a wired access point connected to its switch, allowing laptops to join the same VLAN as the wired PCs.
Yeah, and so here once again we can see that we got the reply, meaning that it does have access to the internet. Because it'll take us a little longer to get all four. Again, we'll just stop it a little short and move on to the next test.
I have a domain name called smuserver.com, so users can connect by name instead of typing IP addresses.
And here again, we can see that we got the reply showing that this does work. Because it'll take a little longer to get all four replies, we're going to move on to the next test.
Next, we'll test the ASA firewall and the router connection that represents the internet.
And here we can see that we got the reply once again, meaning it works. We're going to cut the test short again, just so that we can finish all of them.
To sum it up, our smart campus network successfully connects multiple SMU buildings through VLANs, DHCP, DNS, wireless access points, and an ASA firewall that connects to the router for external access. All major tests passed. Devices can get IPs automatically, reach other buildings, and access the internet securely. Overall, this project helped us understand how routing, switching, subnetting, and security all come together to create a reliable real-world network.
And there's one more thing that we just wanted to show we forgot. You can see here I'm in static. Whenever I go to DHCP, the laptop will be assigned and it will be assigned a default gateway, a DNS server, an IPv4 address, and a subnet mask. This happens for every laptop, every PC across the buildings. And we also just wanted to show you the physical layer. Here we have the four buildings. You can see how they're connected to one another. Each building has laptops and printers. The printers are also usable, but for the sake of time, we'll just skip over that for now. Laptops, printers. The main building has the main server, the main router, the core router, the IoT server, and it has all of that. And yeah, that's just what we wanted to show you. That's pretty much it.